Hi, I'm Karen Riggs. I'm the county engineer for Cochise County.
And my name is Cyrus Miller. I'm a project manager, a hydrologist with J.E. Fuller Hydrology and Geomorphology.
Looking behind us to the watershed that's bringing water down to this project. Those are the Huachuca Mountains in the background. Ash Canyon is one of the canyons you can see. And behind us you can see that there's no channel here. This is just sheet flow area. So the water is just spreading and running all the way from the top of those mountains down here and into what we'll show you in just a few minutes, which is a basin that collects all this sheet flow, routes it underneath Palominas Road and into 13 recharge basins that infiltrate the water as it gets closer and closer to the San Pedro River.
And what you can see behind us is the watershed measures about 7.5 square miles. And if you can imagine the amount of water that runs off 7.5 square miles, it's quite a bit. And so we've designed our project to handle not only the flood and the flood control aspect of that, but also to slow down and meter the water out into the optimal areas for recharge of the aquifer.
And we'll show you as we go through this tour that you're going to take every item that has gone into the design, why it was put there, and how we are instrumenting and monitoring this project so that we can learn every bit of information we can from it, and also to very clearly show how much recharge we're accomplishing with our project. Behind me you can see a big wall and the tops of some school buses. This is the Palominas Elementary School, and this area has had flooding problems for about as long as anyone can remember. The wall that you see was actually built by the county to keep the floodwater out of the school.
So what you see behind me, the rocks in the background, is what we call the primary spillway or a riprap chute. The purpose of it is to take the water, collect the water from the upland, from the schoolhouse wash as it flows towards the project, and collect and convey down elevation in a short amount of time, short distance, without causing erosion, and then transition the flow back into sheet flow as it moves its way across the basin, across the detention basin, and towards the primary outlet structure.
We're in the bottom of the main collection basin. This is the depth gauge to show us how deep the water gets. It's got to get to 3 feet before it runs over the top of the main inlet, which we'll show you in just a minute. After 2 monsoon seasons, we've never gotten higher than a little over 1.5 feet in the basin.
I'm standing here at what we call the primary outlet feature of the detention basin. It's a combination weep hole and grate inlet structure, much like you might see a grate inlet structure on a roadway or in a parking lot. The water level rises, and if it gets high enough, this is a 3-foot elevation, a 3-foot depth in the basin. If it gets high enough, goes over and spills over into the grate and into the box, which is outlet by the 3 36-inch CMP corrugated metal pipes that flow through the main berm of the detention basin. What we see here behind me is the secondary outlet, which is an overflow, emergency overflow, a weir that outlets the flow if the elevation was to get too high to overwhelm the system of the detention basin. The primary outlet is the culvert system that's behind me here. The 3 CMP corrugated metal pipes that outlet flow to the channel, and they all provide what we call the outlet of the detention basin.
I'm in front of the box culverts that go under Palominas Road. These were actually built before we designed the project. There were 2 very small box culverts here that very frequently overflowed and caused flooding problems both on the road and then downstream as it spread. So the flood control district got design, and we ran the construction project to replace those small box culverts with 4 10-by-4 box culverts. This will start our tour of the actual infiltration basins of the part of the project. We've captured all the stormwater on the west side of the road. Now we'll be walking down through 13 basins that are the heart of the infiltration and the recharge. Every basin is instrumented. We're gathering data from every one. And Cy will tell you a little bit about how we actually came to put the recharge on this side of the road.
During design and during analysis, we determined that the east side of Palominas Road and the constructed county flood control channel there was the optimal area for infiltration. Not only was it better soil, more conducive to infiltration, but it was also closer to the river that you can see behind us here. So we leveraged the existing county facility, the existing constructed county flood control channel, and augmented it with the infiltration basins using the weir walls, concrete weir walls that allow for the water to cascade slower velocities down the system and infiltrate into the subsurface. Inside of those infiltration basins, we've got different types of infiltration augmentation features, we might call them. Dry wells, both single cell and dual cell, and then also infiltration trenches, trenches filled with coarse washed gravel below the subsurface.
And so every augmentation type is instrumented, but we have several basins that don't have additional infiltration methods. Those are also instrumented. Every basin down here is instrumented so that we can analyze exactly what recharge we're getting in which basin at what time.
And so as we analyze the data that we collect, we can hopefully determine which features, which augmentation features, if any, are more appropriate from a cost perspective and from a benefit perspective for infiltrating water into the ground, and apply those for future projects.
And you know, this was the first county recharge project. Since that time, several different properties have become available through partners. We've done initial engineering analysis on several of those, and so everything that we're learning here is going into our toolbox for future design of recharge projects in the basin. This is one of the monitoring wells that was put in as part of the project. We'll see as we go down the channel toward the end a well that we started monitoring before the project was built that was already in. This was put in as part of the project to monitor depth to groundwater. So it's just like a regular well, except that we're not pulling any water out, but it is instrumented so that we can tell things about it.
This has a pressure transducer that's down into the well, down into the casing, that we can record water depths essentially, measure the depth or the elevation of the water table. This actually is the point where we've noticed the most profound and the most distinctive rise in elevation of the water table as a result of the project. This is kind of in the middle. We took a look at the detention basin portion, and we're going to look at the channel downstream, but this is where we've noticed the greatest rise in water surface of the aquifer since the project was put in. What we have here is what we call an instrumented borehole. This is essentially a well that's been advanced down into the subsurface. Instead of taking water from the ground, we're measuring the soil moisture at different levels within the subsurface.
We're standing at one of the single chamber dry wells in Basin 6 of the 13 basins that comprise our actual recharge portion of the project. This measures the flow that comes in and how effective these are compared to the other basins.
This dry well is much like you might see in a parking lot or in a retention basin. They're used in Arizona quite frequently. They're used a lot in the Phoenix metro area. What this is essentially a well that's drilled, a boring that's advanced to 10 feet above the water table. The boring material that's removed is replaced with coarse gravel, and then as the water comes in, this accepts the stormwater and infiltrates it into the subsurface faster than it might otherwise infiltrate into the native material that we have on site. What we have here is another pressure transducer. The PVC pipe houses a pressure transducer that's down in the subsurface. At the top is the data collection point. This device, much like the other pressure transducers in the system, measures depth and records that depth over time. And from that, we can determine the effectiveness of the infiltration trench, how fast it's infiltrating the water into the subsurface.
This is a infiltration trench. This is one of the tests that we did in some of the basins. In this basin we actually have two. There's one at each end of the basin. You're looking at one at the downstream end. And what we're testing here is kind of a low-tech approach that we're testing against the dry well notion. So Cy, can you tell them about how we did it?
Yeah, this is a trench. Basically what you're seeing is the top surface of the trench. Beneath us we've got a 12-inch layer of this coarse rock that you see here, what we call riprap. And then beneath that we've got 5 feet in depth of coarse washed gravel. And that coarse washed gravel is intended to promote infiltration, accelerate the water as it gets down into the subsurface. It infiltrates a lot faster than the native dirt would otherwise. And the riprap cap is intended to prevent erosion, and the coarse washed gravel underneath is intended to promote infiltration. We actually, during construction, the contractor notified us that they had encountered some more suitable material for infiltration, some what we call coarse-grained soils during construction, and we moved some of the locations of these basins that I had laid out during construction, or during design rather. So we adapted to fit the site conditions that we encountered once we started digging.
It was interesting. We did have a really good relationship with the contractor, who was quite excited about the project. And as Cy said, they said, hey, we think we found a better place for your infiltration trench because you'll get better infiltration in the soil right here. So we took advantage of them being on site, every minute of the project. And in the type of infiltration that we're doing and in the desert environment, the enemy of recharge is evaporation. Because we have so much evaporation naturally here, you want to get the water you want to capture below the ground surface as soon as possible, because every hour that it's ponding above the surface, you're losing part of it to evaporation. So that's why the infiltration trenches, that's why the dry wells, in addition to just the basins, we're gathering the data to find out how can we be the most efficient at putting that water underground quickly. We're at the dual chamber dry wells. We've looked at the single chamber dry wells already. This is a pilot project, so one of our goals was to test a bunch of different recharge methodologies and see what really worked best here, because what we're doing here is pretty different. We're looking at recharging sheet flow stormwater. We've looked at where it settles in the big basin, but we're still looking at how we best take that slow-moving water and recharge it. So these are the dual chamber dry wells. So you'll have a chamber under here. The water flows in, flows through. The difference between this and the single chamber dry well is that in the bank up there, behind the yellow pipes that you see, is another chamber sunk. And so the water comes into this one, overflows, and fills that chamber, and we have infiltration in both places. So with the dual chamber, we're looking to see if we gain any benefit by having the second chamber that's more free of sediment.
This right here is a standpipe that holds the recording device, a pressure transducer that's installed in the dual chamber dry well. This device and the data that's we're able to record with it measures water depths. From those water depths, we can determine the effectiveness of the single chamber, the primary settling tank, and also the dual chamber, the primary settling tank, and then the dry well. how much water is getting into it and how fast it's infiltrating into the subsurface.
We're standing in a basin without any additional infiltration devices. Of the 13 basins in this channel, we've got some that are plain, some with single dry wells, some with dual dry wells, some with infiltration trenches. We're comparing the data we are gathering continuously on all of those to compare their effectiveness.
All the basins are monitored. We've got pressure transducers at all the basins, and where there are additional augmentation features for infiltration, we've got monitoring devices on those as well. We're comparing the data, and I think that we're going to find that some of the augmentation features that we chose during design will prove to be more effective than others. Some will prove to be less effective than others, and we can take that learning and that information onto the next project and apply that for design the next project.
So we're constantly learning on this project. We're gathering information. We've already kind of gotten an indication that the infiltration trenches at a much lower cost and lower technology infiltrate just as much as the dry wells do, which gives us some more information on our next recharge projects. And this being a pilot project, all the data that we continually gather, the analysis that we do, part of the purpose is to spread this information to other projects, not just in our area, but other similar areas, so people can benefit from the work that we're doing here.
We're also teasing out the differences in performance between the single cell dry wells and the dual cell dry wells. We've determined that for the cost, the single cell dry wells may be more effective than the dual cell dry wells. And we've also taken that down a notch to say that we may look at something even less elaborate and less costly than an actual dry well. Maybe we could just put in something a lot simpler and not involve such heavy construction and increased costs.
The other thing we're doing here is we're logging and putting together what it costs to operate and maintain a system like this, because nobody has a system like this. So that's part of the pilot project as well, is how often are we going to have to clean out a dry well? What is on an infiltration trench, do we try to clean it, or do we just dig another one right next door to it because we've got plenty of room in the basin? So we're gathering data and putting it to use for a lot of different things. Go. We're now at the bottom of the channel. We've looked at all the recharge facilities and the monitoring as the water makes its way down. I just wanted to show you the original piece of monitoring on this project. There's a well in the little house behind me, and it existed on the property when we bought it. And we put some depth to groundwater monitoring on this well about 1.5 years before we did the construction. So we have a baseline groundwater level before the project went in. And this well will continue to be monitored, and it will show us the growth and part of the movement of the groundwater mound as it makes its way toward the San Pedro River. We're standing right now at the very end of the recharge project. We're at the very east end. We're close to the San Pedro River. We've walked down all the way from the intake basin, the overflow, the culvert under the highway, and all the way through the half-mile long channel where the recharge actually takes place. Now we're standing where the water has turned back to sheet flow, runs onto the property behind me, and the next 1/4 mile to the San Pedro River. So we have taken on the very upstream or the west side of the property sheet flow that's wide, shallow, no channels. We've kind of funneled it in, channeled it through all of our recharge structures, and now we've turned it back to sheet flow, and you can see behind me that there's no channel. There's no channel banks, there's no erosion. That just runs quietly and slowly through the grass and makes its way to the San Pedro the way it did before we did any of the project.